Hi BioNerd, this is Modern Chicken channel where you can expand your information about all branches of biology. But before we start, please don't forget to subscribe and follow me on my Instagram. Today's video is about the excitability of a nerve. Before talking about action potential, which I'll cover in the next video, we need to know more about basic definitions of actions or of the excitability of a nerve. In order to understand this, an experiment has been performed on the sciatic nerve of the gastrocnemius muscle of a frog. This sciatic nerve was affected by successive stimuli that have the same duration. That means they all had the same time to affect the sciatic nerve. But what they all differ, or every stimulus was specialized with its own intensity. That means everyone had its own strength, let's say. So we found out that the stimuli that had too small intensities weren't able to achieve the excitability that we were waiting for. For example, here the intensity is only like this 34. So although the duration is relatively long in this experiment, which is different here, which every duration is different from the other, but here we want to study only the intensity. So let's imagine that all of them here were 5, not 5, 3 point, or whatever this is. Let's imagine the duration is the same. Duration here doesn't matter, we're studying only intensity. So when the intensity is too small, we won't be able to achieve the excitability of a nerve. But when we increase the intensity gradually, we will finally reach the intensity that will be able to achieve the excitability. And in this experiment, this intensity is 35. And here we must define rheobas. What is a rheobas? Rheobas is the minimum intensity that we need in order to achieve the excitability of a nerve. Even though the duration is too long, without this intensity, which is at least 35, we won't be able to achieve the excitability. The rheobas in this experiment is 35. And here we must really distinguish between rheobas and threshold intensity. Rheobas is, as we said, the intensity that we need in order to achieve an excitability, or in order to achieve what we need, which is here in this experiment, the contraction of the gastrocnemius muscle. So in order to achieve the contraction of gastrocnemius muscle, at least we need 35 millivolts of intensity. Even though the duration is very high. But on the other hand, threshold intensity is the intensity that we need in order to achieve the excitability, but when we specify an exact time or an exact duration. For example, when we decide that the duration that we want is 3 milliseconds, then the threshold intensity is 35. But when the scientists decide that the duration that we want is, for example, 0.15, then the threshold intensity is 112. Threshold intensity can be changed when the duration is changed, but rheobas is fixed. It's always the minimum intensity ever, the minimum intensity that we need when the duration is very long. After studying the effects of intensity on the excitability of a nerve, now we're gonna understand the effects of duration on the excitability of a nerve. So here we're gonna do the same thing, successive stimuli that will stimulate the nerve, but all these stimuli will be equal in intensity and different in duration, and we will find out the same thing. The too small duration won't be able to achieve the excitability, and when we increase the time gradually, we will finally reach the duration that we need in order to achieve the excitability, which is in this situation 0.1. You can notice here that this 0.09 is too small for anything to achieve, although the intensity is quite big relatively when we compare it with the other intensities. But if the duration isn't at least 0.1, no matter how the intensity how big the intensity is, no excitability will happen, and no contraction of the gastrocnemius muscle will be noticed. So here, the exertion time is defined as the smallest or the minimum duration that we need in order to achieve the excitability of a nerve, which is here, as we said, 0.1. While the useful time here, we must define we must distinguish between exertion time and useful time. Useful time is everything where the excitability can happen. It starts with the exertion time, which is 0.1, and ends up with 3. And 3 here is the basic useful time. So what is between basic useful time and exertion time is useful time, which is here 0.1 and 3. And one might ask, what is the basic useful time? We already defined the useful time, but the basic useful time is the time that the Yobas with the time, or for example here, the duration is 3 milliseconds. Intensity is equal to Yobas, which is 35. So the basic useful time is defined as the duration that we need in order to achieve excitability when the intensity is equal to their Yobas. Now we come to the definition of chronaxy. Chronaxy is the duration that we need in order to achieve an impulse when the intensity is equal to the Yobas, but this time multiplied by 2. Chronaxy is not shown here, but if it were shown, how would we calculate it? First of all, we have already the Yobas, which is 35, 2 and 35. Then it's 70 millivolt. So here 70 millivolt is not seen, but if it were, the definition of chronaxy is the duration when the intensity is 70. So it's in general the duration that we need to achieve the excitability when the intensity equals the double of the Yobas. After we mentioned the basic concepts that we needed in order to understand the excitability of the nerve, we're gonna move to the relationships between these concepts. We'll start with the easiest one, which is the relationship between intensity and duration, which is so clearly inverse. So there is an inverse relationship between the intensity and the duration of the stimulus. As we can see here in the table, when the intensity is too small, like 2 millivolts, it will take more time in order to achieve the needed excitability. And that means the weaker the intensity is, the longer it will take in order to achieve the same effect of a big intensity but with shorter time. So as we see here, when the intensity is relatively high, like this, 10 millivolts, then it will be strong enough to achieve the excitability without taking too much time. It will need only 1 millisecond. Here we're studying the effect of temperature on the intensity and duration, or on the chronaxy and Yobas. But before moving to the next table to understand how temperature can affect the excitability of a nerve, because we haven't mentioned that before, we'll need to understand here the table as we relating on the definitions or the explanations we made. Here you have the lowest intensity that we need in order to achieve an impulse, which is 2. And that means these two will be the Yobas. So Yobas equals 2. So, okay. We define the chronaxy as the duration that we need in order to achieve an impulse when the intensity is Yobas multiplied by 2. Here the Yobas is 2. When we multiply 2, it's 4 clearly. So here it's 4. And the duration when the intensity is 4 is 1.5. That means the chronaxy here is 1.5. And that's what we need here. So when you understood how we can find the Riobas and Chronaxi when the table is given, you actually understood my explanation. After studying the inverse relationship between intensity and duration, we'll move to the inverse relationship between chronaxy and excitability. Clearly, when the chronaxy is high, that means when the duration that we need, when the intensity is equal to the Riobas, is longer than other situations, then the excitability will be low. Why? Because the duration is too low. That means the cell needs too much time in order to achieve the impulse, and that means the excitability of this nerve is low. But when the chronaxy is small, that means this cell doesn't need too much time in order to achieve the impulse, and that means the excitability is higher. So there is an inverse relationship between the excitability of a cell and its chronaxy. And the same with Riobas, which is the intensity. When the excitability of a nerve is high, that means it won't need a very high intensity in order to start making impulses. So when the excitability is high, we will only need a small intensity in order to achieve the impulse. So higher the excitability is, the lower Riobas and chronaxy are. And about the temperature. When the temperature is high, that means there are lots of biochemical actions that are happening inside the cell. And that means higher excitability. Then how do you expect the relationship between temperature and excitability? It's absolutely not inverse. Because the higher the temperature is, the higher the excitability is. But the inverse relationship is between temperature and Riobas and temperature and chronaxy. Because as we said, when the temperature is high, the excitability is high. But when the excitability is high, the temperature is low. And that's, when the excitability is high, the Riobas and chronaxy are low. And that makes the Riobas and chronaxy low when the temperature is high. Maybe you just got swayed with this too much idea. So this will clarify everything for you. For example, here, when the temperature is 20 Celsius, the Riobas was 2. Why? Because here we have a higher temperature. That means there are lots of biochemical activities that are happening, and that makes the excitability of the nerve higher. That makes the intensity that we need in order to start making impulses lower than this situation. When the temperature is only 10, then we will need 3 millivolts in order to start achieving impulses. So we can notice from this that when we increase the temperature, the Riobas is reduced, and the same with the chronaxy, of course, because when you decrease Riobas, we decrease this value, which is Riobas multiplied by 2, and this will absolutely decrease the chronaxy. And with that, we covered all what we need to understand nerve excitability. Next video will be about action potential.